Hi, and welcome back to part two of lecture one on evolvable hardware introduction and digital hardware. So I want to progress on now from the introduction really and start talking a bit more about digital hardware and how we might apply computational techniques to it to produce some evolvable hardware. So let's first of all think about how we might do this, how we might actually use evolution in design. So I think there are three, if we think about it, there are three obvious ways of where we might use evolution on hardware, or how we might do. So the first one is in a program. So in actually a basic program. So I think Steve's already done a bit of CGP with you, and CGP allows you to create programs in an evolutionary loop. So that's one way of using evolution for design, and it could be to do with hardware. Probably the least of the three that we're likely to do. The second one is actually having a model of the hardware. So you'll all be familiar with SPICE, if you think back to the first year, and in our case, HDL, VHDL could be Verilog, but I think most of you have come across VHDL in previous years on your course. So what we could do is we could apply an evolution, so put a SPICE program or a VHDL program within inside an evolutionary loop. And by doing that, and by changing the parameters, maybe of the size of the transistors in SPICE or various other components in VHDL, we could actually change the hardware model. And then finally, the third of these is actually using some real hardware. So actually using physical hardware to do those. So those are the three divisions of how we might use evolution in hardware design. As I said, really, we're going to talk a little bit more detail about these last two, really, of either models or actually the physical hardware. So the first one, let's talk about how evolutionary hardware is quite often identified, and we talked about this in part one of this lecture when we talked about extrinsic or intrinsic evolution. So this cartoon is a description of extrinsic evolution. So this is done off chip. Okay, so we start off with this is kind of a consistent with most of this. We've got our favorite evolutionary algorithm, if you have a favorite evolutionary algorithm. So this could just simply be a GA, a genetic algorithm that's running a population. And in this case, the population could be a series of chromosomes of binary digits. It doesn't have to be binary, of course. It could be integer or float or some other representation, but I think in this case, it's easy to think of these as being a binary representation. And each of those chromosomes, so each of those could be converted into a circuit description let's say in SPICE. Let's say that we're going to convert these into SPICE. So these represent various components in your SPICE circuit. So convert these into a circuit description. We've now got models of the circuit, and we can simulate those models. So if we've got it in a transistor representation that fits nicely into SPICE, we can run some SPICE simulations, which ultimately then give us a response for our circuit. So how good is our SPICE circuit to do a low-pass filter, for example? Let's say we're trying to get evolution to evolve a low-pass filter. So we've got our responses, we've got our target response of what we want to meet, the parameters of our filter that we want to meet, and then we can evaluate each member of the population back into our evolutionary algorithm, which will then provide some selection mechanisms, some variation in those to produce a new population of chromosomes that will then go back into our loop. Okay, so this is extrinsic evolution, where we're doing things offline. The other part that we talked about that I mentioned in part one is intrinsic evolution. So where we're doing things on chip. So actually you'll see the left-hand side hasn't changed. So we've still got our GA that's running. We've still got our chromosome that's being produced from the algorithm, the population of individuals. But now what we do is we convert to a circuit description, which, let's say this is an FPGA, which represent a configuration bit stream that's going to configure our hardware, which we then run again to get a circuit response for each of the members of the population, which we can then feed back into our evolutionary loop to produce the best ones and use those as parents to produce the next set of chromosomes, etc., etc., around the loop until whatever your stopping condition happens to be. So extrinsic and intrinsic evolution, off-chip and on-chip, are the two common ways of doing evolution on hardware. Okay, so let's now talk a bit more about digital. So as I've said here, some basics of digital design. And actually, almost all digital design, you can kind of reduce down to this very basic circuit where we've got some sequential logic, or in this case, registers or D-type flip-flops, but let's think of them as registers, okay, which are clocked to drive data between the different registers. And typically between the registers, we have some combinational logic, which does some processing for us before we store the next outputs into the next registers, etc., all driven by these clocks. And of course, we're all very aware that the combinational logic, of course, is made up of lots of logic gates, of variations of logic gates to do the circuit. So, at least for the purpose of this lecture, we can think of digital basics as being like that. And just to give a few examples, so a simple counter, we've got some combinational logic, which maybe builds up to be an adder, and we've got a register or registers that's keeping that the output of the adder, and then feeds back into it as we do our count +1 each time we go around the loop. So a very simple counter, but again, combinational logic with registers in between. Finite state machine, again, is very similar. You'll all be familiar with finite state machines, where we've got a series of registers, and actually the next state logic, the input and output logics, are typically made up of sequential logic circuits, of logic gates with our registers between those. And a slightly more complex example that you'll be familiar with is a typical pipeline microprocessor these days, where we've got registers between each stage of the pipeline, and then within the pipeline we've got combinational logic that's actually doing the processing for us before we store the data in the registers. So all of these follow this idea of register logic structure that I talked about before. So that's kind of what we're working with when we then come to think about, okay, how can we make these evolutionary circuits? How can we create evolution from these circuits? So the first thing, let's think about configuring combinational circuits. So how are we going to come up with a system where we can configure combinational circuits? And of course, what we're not talking about is having discrete logic circuits where we're changing the wires around to do that. Not very autonomous. But we already know about this. So if we think to our FPGA systems, okay, in those it's not actually implementing the logic in gates. It's actually doing it, if you remember, within a piece of RAM, within a small piece of memory. And what we can easily do is, for any combinational circuit, we can store into the RAM the output of the table, of the truth table, and then we address it effectively with the inputs. And for a given address, we've got what the output should be. And so this piece of RAM is doing the same job as if we'd wired up these gates to do that. So in FPGA systems, we're typically used to calling these lookup tables. Okay, but that's what it is. And of course, for reconfiguration, if we want to reconfigure this circuit, which is represented in this piece of RAM, all we have to do is change some of these bits in the RAM, and we've effectively got a different circuit. So it's really quite easy for evolution for our chromosome that we saw in a previous picture, we can just change within evolution, can just start changing these ones and zeros, which go into the RAM, which effectively change the combinational circuit. What about connections? What happens if we want to do a different connection? Well, again, we're used to this with multiplexers. Yeah. Okay, so we know, we're very aware that given a configuration bits, in this case 3 bits, okay, we can actually connect any of the inputs to the output. Okay, so we know that in circuit diagram terms, it looks something like that, where we've got a control bits, a number of inputs, and 1 output. So this component actually allows us to select the routing of one of these to this output, which is then, if you imagine this is connected, this is combinational logic, and this is connected to combinational logic, then we're actually changing the configuration of our hardware. And the previous picture showed us how we can actually change the functionality of the hardware. So with those things together, and again, what evolution would do is this ABC would be part of the chromosome, which evolution could change to reconfigure the circuit. Okay, so if we want to do this in practice, it's not quite so easy to do it right down at the FPGA fabric level. So I think we've all used FPGA design tools, and they're not really very well suited for doing the sort of things I've just talked about. So what typically is done, and what I'll show you an example a bit later is done, is we can take the FPGA fabric, CLBs and RAM, embedded RAM, IO blocks, etc., but then we can abstract up a level. So we can design a circuit from these basic blocks, which gives us something that's more suited for our evolutionary system. So this we might call a reconfigurable cell. And I'll talk about this in the next slide. And then we might have a system on it. So that's the middle level on this diagram here. And then we at the top level, we have lots of these cells that build up a much bigger cell array. And this is what our evolutionary program would work on. It would work on something at this level. So let's look at a bit more detail of these two systems. So here we've got as I said, if we're imagining we're doing this on an FPGA. Okay, so what we're doing is we're creating a virtual reconfigurable circuit, which we can run on the FPGA. So what we've got here is our reconfigurable input. So this reconfigures the connectivity of our circuits. And we've got a block of RAM, which is actually providing our combinational circuit, our logic function within our system here. Okay. And in this particular one, and this is a kind of a random size, we've chosen that there are 4 bits to control each multiplexer, and we've got an 8-bit RAM on there. Okay, so if you add those up, so this reconfigurable circuit or cell actually has 20-bit reconfigurable register. So that's what the Evolvable system would look at. And so yeah, we've got 8 bits for the RAM, for the function, and then we've got 4 bits for each of the multiplexers to allow us to reconfigure the system. And then what we can do, as I said, is we can then, so each cell here is one of those. And so we could have, in this particular case, 8 by 5. I mean, that it depends how big your FPGA is, of how big you could actually, how big this cell array could be. And what we've done here is we've pre-configured it so that for the first column, its inputs come from the outside, from the input data. Okay, and this shows we can either have the input data or the not of the input data. So we've inverted it. So you can choose from which your input goes into the cells. And then for the next columns, what you'll see is that they loop back to the column before them. So in this case, the red. So these inputs come from the outputs of these cells, and these inputs come from 1, 2 back. So in this case, for column 1, 2 back is actually also the input data. If we look at column 3, then it either takes the input from column 2, which is the red line, or column 1, which is 2 back from it. So that, again, this is just a design decision. There's nothing particularly special about this. And so this actually, for this whole cell array, it has 800 configuration bits. And this would form part of the genome that the evolutionary loop would then work on. Okay. And then again, depending how big your FPGA is, so each of these cell arrays, which is one of those, you could have a number of those. So in this example here, and we'll see this used later, and we've actually got 8 cell arrays running in parallel on one FPGA. We've got the input vector where the data is coming in. We've got some extra RAM here, which allows us to say, okay, well, this is what we want to compare the outputs from these arrays to try and get a match of whether the output's working or not. And we can mask which bits we want to do with that. So these are a few details which I guess aren't too worrying for us for this. But what this does do is it allows us to have a fully reconfigurable, evolvable array on an FPGA. Okay, so that's the end of the second part of lecture 1. Looking at how we might do stuff on a digital design. So again, as at the end of the first part, there's a couple of papers there if you want to ever read. They're quite interesting papers. I'm slightly embarrassed that one of them's got my name on it, but anyway, they're papers that you might want to ever read, either immediately after this or at some point in the next few days to do that. So I encourage you to do that. And a couple of questions for you to think about before you look at part 3 of this introductory lecture is, so what actually evolvable algorithms might you use for evolvable hardware applications? So ever think of the ones that you've been talking with Steve and the ones that you've been looking at in labs to see which ones might be used. And why do you think the ones you thought of are good compared to others that you're aware of? So what's the differences between those things? Okay, so that's the end of part 2, and we'll get on to part 3 and the final part of the first lecture that will be coming up. Okay, thank you very much for that.